Okay, let's unpack this. We have a set of source materials that takes us on an absolutely extraordinary journey, spanning, well, the deepest history of theoretical physics, from the musings of Sir Isaac Newton all the way to the newest cosmic discoveries, and even the immediate practical search for lunar comfort.
It's an amazing collection.
The sheer breadth of knowledge we have to process today is staggering.
It truly is. And the mission of this deep dive isn't simply to, recite a collection of facts about black holes. It's an intellectual exercise.
Right.
Understanding why these gravitational monsters are the central linchpin, the ultimate key to unlocking the next great theoretical leap in physics.
Right.
Black holes are the collision point where our two dominant foundational theories, general relativity, which governs the very large, and quantum mechanics, which governs the very small, meet, and currently absolutely refuse to play nicely.
And that friction between GR and QM is the ultimate goal, isn't it?
Mm-hmm.
The holy grail of modern physics. It's where the universe demands a better theory. So here's our roadmap for you. We are going to cover the surprising pre-Einstein history of the black hole concept, which was quite astonishingly ignored by the scientific community not once, but 3 times over 2 centuries.
It's an incredible story of scientific resistance.
Then we'll get into the truly exotic nature of rotating space-time and the bizarre geometry it creates, the quantum mystery of evaporating black holes, Hawking radiation, and finally, we'll dive into brand new astronomical evidence that is currently challenging our existing stellar theories, plus a necessary look at the high-stakes, practical challenges of the new lunar race.
So let's start at the very beginning, with the simplest physics imaginable.
The foundation for the black hole concept is substantially older than Einstein.
Oh, much older. In fact, the mechanics developed by Sir Isaac Newton were perfectly capable of describing the critical condition necessary for such an object to exist.
But he never did he? The sources point out that Newton himself never allowed his imagination to make that final leap.
He didn't, and it all starts with motion and escape. Newtonian gravity and mechanics were phenomenal tools for calculating trajectories.
Right. They defined orbits, which require an object to achieve the first cosmic velocity, enough speed to fly around a massive body without crashing.
And then they defined escape trajectories, which require the second cosmic velocity.
Enough speed to flee the massive body altogether.
Correct. Newton's universal law of gravitation was simple, elegant, and immensely powerful. It could describe the movements of planets, comets, and cannonballs with precision. He possessed all the theoretical machinery required to calculate a critical gravitational field where the escape velocity would become so high that nothing could escape.
So what held him back?
Well, the sources note that Newton was famously cautious. He was meticulous, preferring to avoid speculating beyond what could be directly observed or inferred from immediate data. He built the foundation, but he refrained from placing the final, most speculative brick on top.
So if Newton held back, who stepped forward? Who were the true but repeatedly ignored pioneers who first imagined these dark objects that trap light?
The first person to publish this astonishingly modern idea was an English polymath named John Michell in the 18th century. He presented his work to the Royal Society.
And this is foundational because Michell didn't just speculate, right? He fundamentally understood the core physics using only Newtonian tools.
He absolutely did. He proposed that an object could be so massive and compressed that its gravitational pull would prevent light corpuscles, which was the term used for light particles, or, quanta at the time, from ever escaping the body.
And the fact that he actually crunched the numbers is what makes his work so powerful even today.
Indeed. Michell calculated that if you were to compress the sun's entire mass down to a radius of a mere 3 kilometers, or even more strikingly, compress the Earth's mass down to just 1 centimeter, the resulting object's escape velocity would equal the speed of light.
So nothing, not even light itself, could get away.
Nothing could achieve escape velocity from such a compact star.
That is an astonishing calculation for the 18th century. So if the math was solid, why did the scientific community just ignore this breakthrough?
Well, the issue wasn't the math, it was the physics. The result was considered pure mathematics because nobody could conceive of matter being compressed to such fantastic densities. It defied all known understanding of material strength and constitution.
They just couldn't imagine it.
At the time, physicists lacked the theoretical framework, namely an understanding of atomic structure and subatomic forces, to imagine anything remotely that dense. So it was dismissed as an elegant but impossible curiosity.
And then the idea gets a reintroduction but still fails to gain serious traction.
That brings us to Pierre-Simon Laplace, the great French mathematician and astronomer. He reintroduced Michel's concept, though perhaps curiously, without attribution, in the first edition of his very popular science book, System of the World.
So this groundbreaking idea reached a wide popular audience rather than just being confined to a small academic journal.
Exactly. But here's the profound irony that speaks to the scientific culture of the time. Laplace included this paragraph about small, incredibly compact bodies that wouldn't let light escape in his first edition. Yet in subsequent editions, he completely removed the section.
He took it out. Why?
The sources suggest he did this because he believed the concept was unworthy of a serious scientist's attention. It was too speculative, too close to science fiction. So for the second and third time in history, this brilliant idea of a dark star was buried.
It's amazing to think that the concept of something trapping light was known and dismissed, long before the complex machinery of modern physics arrived. The Newtonian black hole was simple, just immensely strong gravity.
Right. But when we get to the early 20th century and Einstein's general relativity, everything changes.
It becomes a whole different ballgame.
General relativity, published in 1915, made the physics of these compact objects infinitely richer. With Newtonian mechanics, a black hole was simply a point of extreme mass. With GR, we begin to understand how that extreme mass distorts space-time itself.
The analogy from the sources is perfect. Newton gave us a black and white photo of gravity. Einstein gave us the full color photo, complete with distortions of time and distance.
It's a great way to put it. GR demanded that we consider how the geometry of the universe itself is warped by mass and energy. And that warping is what transforms a simple calculation into a profound puzzle. The black hole then becomes the ultimate proving ground for GR.
It's where we test the limits of the theory.
Precisely. We investigate black holes hoping to find weaknesses or deficiencies in general relativity itself. Finding a deviation from GR's predictions near a black hole would be the strongest possible clue on how to construct a new, unified physical theory.
But to even begin testing GR, you first have to solve Einstein's notoriously complex nonlinear field equations.
And that's the hard part. I mean, the mathematics of GR is incredibly intense. It's not like Newton's simple EFMA.
Not at all.
Not at all. Einstein's equations are 10 coupled, nonlinear partial differential equations. They are incredibly difficult to solve, and in fact, most of the universe's situations are still unsolvable in a closed form. It takes either heavy computer power or simplifying assumptions to make progress.
And the first person to actually solve those equations for a simple case, providing the foundation for everything that followed, was Carl Schwarzschild, doing this pioneering work in the unlikeliest of places, the trenches of World War I.
Carl Schwarzschild was a brilliant figure, a German physicist, mathematician, and director of the Potsdam Observatory. Despite his stature, he was conscripted during WWI and worked on ballistics and optics while serving on the Eastern Front.
So he's doing this work while literally at the front.
Yes, while suffering from a rare skin disease that would eventually kill him. It was there that he did this breakthrough work on stellar dynamics and found the first exact solution to Einstein's field equations.
Which is just incredible.
Tragically, he died in a military hospital in 1916 before his revolutionary papers were fully digested by the wider physics community.
And he solved the equations for the simplest possible black hole. Non-rotating, point-like, and perfectly spherically symmetric. What does his solution predict about the geometry around this static mass?
His solution defines several crucial radii around this compact, non-rotating mass. Moving inward, the first significant boundary is the photon sphere. This is the radius where light is so curved by gravity that it will endlessly orbit the black hole, neither escaping nor falling in.
That sounds like a terrifying orbital highway.
It is, and it demonstrates how gravity truly warps the geometry of light. But the most significant boundary he identified was the inner radius, the event horizon, also known as the Schwarzschild radius.
The point of no return.
The boundary where the escape velocity equals the speed of light. Any object, particle, or photon crossing this boundary cannot ever return.
And here's where we encounter the monumental irony for the third time in history.
Absolutely monumental. The formula Schwarzschild derived for this critical radius turned out to be exactly the same as the simple Newtonian calculation made by John Michell 150 years earlier.
So they dismissed it again.
Once again, the scientific community looked at the result and, because it matched the old, simplistic Newtonian theory, dismissed it again as a mere mathematical singularity that could never occur in nature. They had GR, a robust new theory, but failed to recognize the physical significance of its solution for decades.
But the crucial added value of general relativity was not the radius itself, but the prediction about time.
That's the key difference. GR revealed the effect of extreme gravity on the passage of time dilation. If we, as external observers, watched an object falling into a black hole, we would see that object slow down drastically as it approached the event horizon.
So from our perspective,
The object would appear to approach the boundary infinitely slowly, taking an infinite amount of time to reach the point of no return. Its light would redshift, meaning its wavelength would stretch until it faded out completely, never truly witnessing the moment it crosses.
but for the person falling in, it's a different story.
Exactly. For the person or particle falling in, they cross the horizon without any dramatic fanfare. Their clock continues to tick. They simply discover too late that all possible future paths lead directly into the central singularity.
Now here's where it gets really interesting. Rotation. The Schwarzschild solution is an ideal case, but nothing in the universe is perfectly still. Everything rotates.
From planets to galaxies, so black holes must spin. We needed a solution for a rotating mass, and that arrived in the 1960s thanks to the New Zealand mathematician Roy Kerr.
And the Kerr solution is the realistic one.
It's the comprehensive and realistic description of a black hole, acknowledging that these objects possess not just mass, but also angular momentum or spin.
And spin introduces the truly bizarre phenomenon of frame dragging, or the Lenz-Thirring effect. Could you help us conceptualize what that means for space-time?
The Lenz-Thirring effect is a fundamental requirement of general relativity. It states that a massive, rotating body literally twists and drags the fabric of space-time around it, much like a giant paddle spinning in a vat of molasses. The stronger the gravity and the faster the rotation, the stronger the drag.
So if you're near it,
If you are near the spinning mass, space-time itself is carrying you along, whether you want to move or not.
and that twisting creates an enormous active zone around the black hole called the ergosphere.
The ergosphere is a critical region just outside the event horizon. Within the ergosphere, the frame dragging is so powerful that standing still relative to a distant, non-moving observer is physically impossible.
Impossible.
Space-time is moving faster than the speed of light relative to that distant observer. You can still escape the black hole from the ergosphere, but you cannot stop moving. You are forced to rotate in the same direction as the black hole.
So it's not the point of no return, but it is the point of constant forced motion. It's like stepping onto a moving carousel.
Exactly like that. Imagine stepping onto an extremely fast-moving, flat carousel. You can jump off if you try hard enough, you can escape the black hole, but once you're on the surface, you cannot brace yourself or stop moving relative to the ground because the ground itself is carrying you along. It's an active, dynamic region.
And this rotating energy, this gigantic angular momentum, is not just inert. It can actually be exploited. This is the amazing Penrose process.
Roger Penrose, who won a Nobel Prize largely for his work proving the theoretical inevitability of singularities, theorized that the ergosphere is not merely an energy drain, but an energy source.
Oh, that worked.
His scheme involved throwing an object, say a spaceship or a container of waste, into the ergosphere. As the object is caught in the space-time drag, it is massively accelerated. If you strategically jettison a piece of that object, and that jettisoned piece has negative energy relative to the escaping piece, the remainder of your ship or container can slingshot out with more energy than it started with.
So the black hole itself is fueling your exit.
Precisely. You are extracting the rotational energy of the black hole, proving definitively that black holes are not simply energy graves. They are vast repositories of usable kinetic energy. The black hole slows down slightly, and you gain energy. This was a massive conceptual leap.
And this isn't just theory. The sources mention that frame dragging is weak, but measurable, even around Earth.
That's a crucial point for validating GR. The frame dragging effect is subtle around a slowly rotating mass like Earth, but it has been experimentally verified using dedicated missions like Gravity Probe B.
So they actually measured space-time twisting.
These satellites used ultra-precise gyroscopes to measure how Earth's rotation subtly drags and twists the space-time around it. The results provided a necessary confirmation that the complex mathematics of GR describes real physical phenomena across the universe.
The realization that black holes might not be permanent gravitational graves started even before Stephen Hawking's definitive breakthrough work. The sources highlight an important precursor.
Yes, we have to recognize Yakov Zeldovich, the founder of relativistic astrophysics in the USSR. He was the first to qualitatively suggest in his lectures and seminars that black holes might actually radiate energy.
So the idea was already floating around.
Zeldovich was an intellectual powerhouse, a truly colossal figure in Soviet physics. He was known for scattering brilliant, radical ideas, often just verbally. One of these ideas, circulating in the late 1960s, was the possibility that, due to quantum effects near the horizon, black holes must emit some form of radiation, fundamentally contradicting the prevailing belief that they only absorb.
And it was Stephen Hawking who formalized Zeldovich's concept and delivered the breakthrough mathematical model of black hole evaporation.
Hawking formalized what we now call Hawking radiation in the early 1970s. The underlying mechanism is where the deep conflict between GR and QM begins, and it requires a dive into the nature of the quantum vacuum.
Right, the idea that empty space isn't actually empty.
Not at all. According to quantum mechanics, the vacuum of space is a dynamic, fluctuating realm of energy where virtual particularly antiparticle pairs, like an electron and a positron, are constantly and spontaneously popping into existence and annihilating instantly. They are fleeting, temporary manifestations of energy uncertainty.
And the key is that they must annihilate instantly to satisfy conservation laws.
Exactly. But the black hole's event horizon acts as the mechanism to violate this immediate annihilation. If a virtual pair forms precisely at the event horizon, the intense gravity intervenes. One particle falls inward, pulled across the point of no return.
And the other one escapes.
The other one escapes. Crucially, that inward falling particle is often described as having negative energy relative to the escaping particle.
That concept of negative energy is always where the explanation gets a little fuzzy.
It can be? Let's think of it this way. The total mass energy of the black hole is the gravitational field. When the inward-bound particle falls in, it effectively steals energy from the black hole's gravitational field, meaning the black hole loses a tiny bit of its total mass. That missing energy is what allows the partner particle to escape the clutches of gravity and become a real detectable particle, a photon, an electron, or another form of radiation.
So since the black hole is losing mass, it is effectively radiating.
Exactly. And this means the black hole is losing mass and energy over time, which implies it must possess a measurable temperature, just like any other radiating body.
That's the monumental implication.
It is. Hawking's formula for the black hole's temperature is a staggering piece of theoretical synthesis. It incorporates the giants of physics: Planck's constant from QM, the speed of light from relativity, and the gravitational constant from gravity. By combining these fundamental constants in one equation, Hawking effectively proved that black holes possess thermodynamic properties, and as a consequence of radiating, they must slowly evaporate over timescales unimaginably longer than the age of the universe.
And the status of that formula in physics is clear based on its resting place.
It is considered one of the great achievements of modern physics. The equation for the black hole's entropy is famously inscribed on Stephen Hawking's grave marker in Westminster Abbey, placed between the final resting places of Sir Isaac Newton and Charles Darwin.
A place among the giants.
That location is symbolic, recognizing his theoretical work as a foundational pillar of modern science.
But despite being considered theoretically sound, the radiation is too weak to detect currently.
Correct. For stellar mass black holes, the radiation is negligible, making them colder than the cosmic microwave background radiation. We would only be able to detect Hawking radiation from extremely small, theoretical primordial black holes, those that might have formed in the chaotic moments after the Big Bang, perhaps with the mass of a mountain or less.
And we haven't found any of those yet.
Those smaller black holes would be evaporating rapidly and would be hot enough to emit detectable gamma rays, but we haven't found any conclusive evidence of them yet. Detecting Hawking radiation remains a crucial, unverified theoretical prediction that would finally provide experimental proof of the collision between GR and QM.
Before we move on to the life cycles of stars, let's nail down the terminology. Who coined the term black hole?
The term black hole was popularized by the influential American physicist John Archibald Wheeler in the mid-1960s. Wheeler was tired of the clunky academic terms like collapsers, dark stars, or dead stars.
They don't have quite the same ring to it.
Not at all. He is credited with introducing the phrase, often attributing it to a student or journalist during a lecture, recognizing its immediate power and simplicity. It's the perfect evocative name. It instantly communicates exactly what it is.
It just stuck.
It did, and it dominated the discourse almost immediately. But the sources do include a great historical footnote. The Russian term Kornaya Dira, which means black hole, was actually used in print earlier than Wheeler's popularization, not by a physicist, but by the renowned Russian science fiction authors, the Strugatsky brothers.
So sci-fi got there first.
The popular imagination sometimes anticipates scientific breakthrough.
To understand black holes, we must trace their lineage. They are simply the most extreme possible outcome of stellar death.
And we can start with the familiar. Low-mass stars, like our sun. Their death process is slow, if beautiful.
After burning hydrogen for billions of years, a star like the sun begins to run out of core fuel. It expands dramatically into a red giant, heating up its outer layers.
Which eventually puffs away into space in what we call a planetary nebula. What is left behind is the small, incredibly dense, and hot remnant core known as a white dwarf.
And white dwarfs are where we first encounter extreme cosmic density, though they aren't fully crushed yet.
They are exceedingly common, but their density is mind-bending. The core's mass is supported only by electron degeneracy pressure. This pressure is the quantum mechanical resistance of electrons against being crushed too close together, a kind of super strong bumper car effect.
The numbers are staggering.
The sources highlight a startling figure. A cubic centimeter, about a thimbleful, of white dwarf material weighs 5 million grams, or several tons. You've taken the sun's mass and compressed it down to the size of Earth.
But that internal resistance, that electron degeneracy pressure, has an absolute ceiling, a point beyond which gravity wins entirely.
That absolute ceiling is the Chandrasekhar limit. In the early 1930s, the young Indian astrophysicist Subramanian Chandrasekhar calculated that if a stellar core exceeds 1.4 solar masses, the electron degeneracy pressure is fundamentally insufficient to counteract the crushing force of gravity. The core must continue collapsing.
And Chandrasekhar faced significant opposition when he first presented this work, didn't he?
He did. When he presented this groundbreaking calculation to the Royal Astronomical Society in Britain, he was publicly ridiculed by the establishment, specifically Sir Arthur Eddington, who refused to believe that stars could end their lives in such an extreme state.
So he had to fight for it.
He was forced to fight for years to prove his result, eventually winning the Nobel Prize decades later for this fundamental contribution. It just demonstrates that resistance to radical ideas is a recurring theme in physics.
So if a star, say, 5 to 10 times the sun's mass runs out of fuel, its core exceeds 1.4 solar masses. What is its violent path to a compact object?
That core collapses violently under its own weight, causing a rapid bounce that generates an enormous shockwave. The star first swells into a supergiant and then explodes as a massive Type II supernova, scattering heavy elements across the galaxy. The remaining dense core remnant is what interests us, and its fate depends entirely on its final mass.
If the core is over the white dwarf limit, but under approximately 3 solar masses, we land at neutron stars.
Neutron stars are the next level of density, where gravity has overwhelmed electron degeneracy pressure, crushing the electrons into the protons. This forces them to merge and create an ultra-dense sea of neutrons.
And these are tiny.
Truly city-sized objects, maybe 15 to 30 kilometers across, but with unimaginable density. To give you context, the density figure is 100 million tons per cubic centimeter. If you took all the traffic on the busiest highway and condensed it into the size of a single raindrop, you wouldn't even be close.
And the sources remind us of the contentious discovery of these objects, which were initially detected as rapidly spinning radio beacons.
That's right. Neutron stars were first detected in 1967 as rapidly rotating radio sources, which we call pulsars, by Jocelyn Bell, who was then a graduate student. Her supervisor, Hugh Hewish, received the Nobel Prize for the discovery, sparking significant scientific friction and criticism over the exclusion of Bell.
A huge controversy at the time.
It remains a major touchstone in discussions of scientific recognition.
Both neutron stars and stellar black holes are, in their purest state, invisible objects. How do we find these dark, compact, gravitational beasts?
We almost always find them in binary systems. They siphon mass from a companion star, a process called accretion. The infalling matter orbits the compact object, forming a rapidly spinning accretion disk.
And the friction in that disk is what makes them visible.
Exactly. Due to immense frictional heating layers of gas rotating at different speeds close to the speed of light, this material heats up incredibly, radiating brightly across the entire electromagnetic spectrum, optical, X-ray, and gamma rays. This signature reveals the presence of an otherwise invisible, massive object.
And often emerging from the poles of these disks are powerful, mysterious jets.
These systems frequently eject the most powerful phenomena in the universe. incredibly powerful, narrow, focused jets of hot relativistic matter along the rotation axis. We understand that high temperatures and the compact object's magnetic field create the pressure to launch this matter. However, the exact mechanism for the extreme focusing of these jets,
Down to just 1 or 2 degrees.
down to a tight 1 or 2 degree angle, remains a major unsolved puzzle in astrophysics.
So if the mechanism is unclear, does that uncertainty impact our understanding of the energy budget of the universe?
Absolutely. The energy output from these jets is colossal. If we don't precisely model the focusing mechanism, we can't accurately predict how much energy and matter is being injected back into the galaxy over cosmic timescales. This, in turn, affects models of star formation and galaxy evolution.
So let's assume we observe an accretion disk with jets. How do astrophysicists distinguish between a black hole and a neutron star when both look similar?
Hypothetically, if we could build a telescope with literally infinite resolution, we could distinguish them. Matter falling onto a neutron star would hit a physical surface, creating a colossal, bright hotspot, like dropping a mountain onto a diamond.
Whereas with a black hole,
Matter falling into a black hole, however, would disappear beneath the event horizon, leaving a region of complete darkness, the black shadow.
but we can't build a telescope that sharp.
As the sources emphasize, given the astronomical distances involved, we will likely never have telescopes sharp enough to see this difference directly, so we rely on mass calculations. If the object's mass exceeds 3 solar masses, we know it must be a black hole because no known force can stop the collapse past that point.
Moving beyond stellar remnants, we shift our focus to the supermassive black holes, or SMBHs, which reside at the centers of nearly all large galaxies.
And our own galactic center, Sagittarius A, is hidden behind immense clouds of dust and gas. How do we see what's going on there?
We use a revolutionary technology called adaptive optics.
That's right. Earth's atmosphere constantly distorts and blurs light, making ground-based astronomy challenging. Adaptive optics systems counter this by using powerful lasers to create an artificial reference star high in the upper atmosphere.
And the telescope watches that artificial star.
By constantly monitoring the distortions of that known artificial source, the telescope's primary mirror can rapidly adjust its shape up to 1,000 times per second to neutralize the atmospheric blurring. This allows us to achieve clear, high-resolution images, specifically in the infrared band, which can penetrate the obscuring dust clouds.
And this technique allowed astronomers to track the movements of stars right near the core of SGRA.
Yes, the long-term observational campaign, famously led by Reinhard Genzel and Andrea Ghez, tracked individual stars orbiting an invisible point with extreme velocity over 30 years. This work earned them the Nobel Prize.
And what did it prove?
The analysis not only conclusively proved the existence of a 4 million solar mass SMBH at the center, but also demonstrated that all the relativistic effects predicted by GR, such as the subtle precession of the star's orbits, are perfectly visible in these movements. GR is literally governing the dynamics of our galactic center.
Now let's get into the brand new, cutting-edge discoveries that truly challenge our current theories.
Yeah.
The intermediate mass mysteries.
This is where theory and observation are actively colliding right now. For decades, we knew about stellar mass black holes and supermassive black holes, but there was a missing link. The intermediate mass black holes, or IMBHs.
Objects from 100 to 100,000 solar masses.
And the huge problem is that stellar evolution models, even accounting for massive stellar collisions, struggle to account for BHs larger than 100 solar masses. Their origin is a major unsolved puzzle.
So what were the leading theories before this new evidence arrived?
The theories were varied. One possibility was runaway collapse, where in the dense core of a globular cluster, massive stars collide repeatedly, forming a single ultramassive star that collapses directly into an IMBH. Another leading idea was the direct collapse model, where giant gas clouds in the early universe bypass star formation and collapse directly into BHs.
But the latest news provides a potential explanation that connects back to a theory predicted decades ago. This is the aha moment.
It is a phenomenal connection. Recent news provides strong evidence of an approximately 30,000 solar mass IMBH orbiting our own central SMBH, SGRA. The fascinating part is the mechanism of its arrival. The detection strongly supports a hypothesis known as dynamical friction.
Can you explain dynamical friction simply?
Imagine a massive star cluster complete with its own central IMBH moving through the denser background environment of the galactic core. As this cluster moves, its gravity subtly attracts and slows down the surrounding gas and stars, creating a kind of gravitational wake behind it.
A drag force.
This wake exerts a drag force, the dynamical friction, which causes the cluster to slowly lose energy and spiral inward towards the galactic center.
So instead of forming in the center, these IMBHs are being delivered to the center by their host star clusters, acting like massive gravitational pebbles sinking into the galaxy's core.
Exactly. It connects a theoretical prediction, dynamical friction, directly to a physical object currently observed, suggesting our galactic center is far more volatile and complex than we previously imagined.
We can't talk about black holes without discussing the images, the seemingly impossible feat achieved by the Event Horizon Telescope. How did they take a picture of something that is, by definition, invisible?
The Event Horizon Telescope, or EHT, is not a single telescope. It's a global network of radio telescopes using a technique called very long baseline interferometry. By linking radio dishes spread across the Earth from the South Pole to Spain to Chile, they synchronize the incoming data, creating one single synthetic telescope dish the size of Earth.
And that gives them the resolution they need.
It allows them to achieve the necessary angular resolution to image an object 50 million light-years away.
Their first major success was imaging the accretion disk around the black hole in M87. Why was that image so important beyond just the visual achievement?
The first image, released in 2019, captured the SMBH in the galaxy M87, a monster at 6.5 billion solar masses. The key importance was that the image of the shadow and the surrounding ring of light matched theoretical predictions extremely closely. This wasn't just a pretty picture. It was crucial evidence validating the no-hair theorem.
The no-hair theorem, a great name. What does it mean?
It's the theoretical idea that a black hole is fundamentally one of the simplest objects in the universe. It has no hair, meaning it is completely characterized by just three properties: its mass, its electrical charge, and its spin. The EHT image confirmed the size and shape predicted by GR based only on those parameters, strengthening the idea that BHs are the mathematically perfect objects predicted by Einstein's theory.
And then they imaged our own, SGRA.
Their second image, released in 2022, was of our own, smaller SGRA.
The black hole is the ultimate example of pure extreme gravity. Einstein predicted gravitational waves ripples in spacetime in 1916. But it took almost a century for direct proof. Why was the detection so elusive for so long?
It took so long because gravity is an astonishingly weak force, about 10 times weaker than electrical forces. While Einstein predicted these ripples, detecting them requires truly massive objects moving at high relativistic speeds, causing powerful high-frequency changes in space-time curvature.
And the distortions are tiny.
Even the most violent events create distortions measured in fractions of the diameter of an atomic nucleus.
We did have indirect proof back in the 1970s, which itself earned a Nobel Prize.
That was the work of Hulse and Taylor, who observed a binary system of two rapidly orbiting neutron stars. They meticulously tracked the orbital period of these stars over decades and noticed that the period was decreasing. The stars were spiraling closer together.
And the energy had to be going somewhere.
The rate of energy loss precisely matched the prediction general relativity made for energy escaping via gravitational waves. This confirmed, indirectly, that GWs existed and carried energy.
Then came the direct detection breakthrough in 2015 using LIGO. This confirmed black holes existed in their purest form, interacting through gravity alone.
This was the culmination of decades of engineering work at the Large Laser Interferometer Gravitational Wave Observatories. These detectors use long vacuum tubes and mirrors to measure infinitesimal changes in distance caused by a passing gravitational wave. The 2015 breakthrough detected the final moments of two black holes, a 36 and a 29 solar mass objects spiraling together, merging and ringing like a bell.
And the energy released during that brief event is almost impossible to comprehend.
The magnitude is staggering. For that split second of the merger, the energy released in the form of gravitational waves was greater than the total electromagnetic energy output of all the stars in the visible universe combined. The merger resulted in a single black hole of 62 solar masses. The missing mass, about 3 solar masses, was converted directly into pure gravitational wave energy, confirming EMCA22 on a truly cosmic, terrifying scale.
The sources note that neutron star mergers are even more valuable to astrophysicists than black hole mergers. Why is that?
When two black holes merge, we only receive the gravitational wave signal, a chirp, but when two neutron stars merge, we receive what is called a multi-messenger event. Because they are physical objects with surfaces made of matter, the collision causes a colossal physical explosion, a kilonova. This explosion sends out electromagnetic radiation X-rays, gamma rays, and optical light simultaneously with the gravitational wave.
So we hear the gravity and see the light at the same time.
Exactly. This rich, simultaneous dataset allows astrophysicists to study the physics of matter under extreme conditions, including how heavy elements like gold and platinum are forged, which are believed to be created during these kilonova explosions. It provides a much clearer picture of the processes.
Looking ahead, ground detectors capture the high-frequency GWs from the moment of merger. What about the future of space-based detection?
That is the goal of the LISA concept, the Laser Interferometer Space Antenna. LISA is a proposed constellation of 3 satellites orbiting the Sun, forming a giant triangle millions of kilometers wide.
So it's a massive detector.
Because of its massive scale, LISA will be sensitive to long wavelength GWs. These are the waves emitted by binary systems as they slowly spiral inward over long timescales before the final high-frequency merger.
This would give us an early warning system for cosmic violence.
Precisely. It would give ground-based observatories a crucial lead time, potentially months or years, to prepare optical and radio telescopes to watch the final violent burst, transforming multi-messenger astronomy into a true predictive science.
Now that we've covered the physics we know, validated by the EHT, LIGO, and decades of stellar observation, let's look at the theoretical edges where math runs ahead of experiment. And let's start with wormholes.
Wormholes, sometimes mathematically referred to as moleholes, are purely mathematical solutions to general relativity. They describe space-time tunnels that, theoretically, offer shortcuts across vast cosmic distances.
That sounds like perfect science fiction, but what's the physics catch?
The catch is enormous: stability. The mathematics clearly shows that wormholes are inherently unstable. The moment any regular matter, a photon, a person, a dust mote, enters the tunnel, the gravity of that mass causes the tunnel to collapse instantly, tearing apart whatever is inside.
So they're useless in practice.
Well, to stabilize a shortcut across the universe and prevent that instantaneous collapse, you would need a form of exotic matter with negative mass energy, effectively acting as anti-gravity.
Like dark energy.
This is where the concept ties into dark energy, the mysterious force that currently drives the accelerated expansion of the universe. Dark energy exhibits anti-gravitational properties. Theoretically, if we could gather and deploy enough of this exotic matter, it could stabilize the tunnel mouth, making interstellar travel possible. This concept was famously leveraged by Kip Thorne when consulting for Carl Sagan's novel, Contact.
Switching gears completely from theoretical warp drives to actual near-term construction. Let's look at the strategy for establishing lunar habitats. The lunar surface sounds utterly hostile.
It is intensely hostile. The surface is unprotected, subjected to extreme conditions. Temperatures swing wildly from a scorching plus 120 Celsius during the lunar day to a freezing next 150 Celsius at night. Plus, there is no thick atmosphere or magnetic field to protect occupants from continuous high doses of radiation.
So the solution is natural shielding. We go underground.
Precisely. Over 200 known pits have been observed on the lunar surface. These are thought to be collapsed entrances to massive subterranean lava tubes or caves. These offer perfect natural shielding, much like Earth's deep subway tunnels or bunkers.
What's the temperature situation inside these tubes?
It's beautiful. Radar scans from the Lunar Reconnaissance Orbiter confirm that the deep areas of these caves maintain a stable, freezing cold temperature of around negative 25 Celsius. However, the most recent computer simulations show something fascinating. Sunlight penetrating near the entrance can heat the immediate surrounding area to a surprisingly comfortable plus 17 Celsius.
That is nearly room temperature, requiring minimal power input.
Minimal input indeed. With just the heat generated by standard equipment and crew activity, a base could easily maintain a comfortable environment of plus 22 Celsius year-round. These lava tubes essentially provide a ready-made, naturally shielded, thermally stable habitat.
Meanwhile, the lunar race is on again. China is aiming for 2030, but the U.S., with Artemis 3, has set an extremely aggressive deadline of landing astronauts by 2026.
The Artemis mission architecture is vastly more complex than the original Apollo program. Artemis 3 requires a highly complicated, multi-launch architecture. The SLS rocket, multiple Starship tankers for orbital refueling, the specialized Starship lunar lander, and then the Orion capsule for the return trip.
That complexity sounds like a recipe for delays.
Audits suggest the 2026 deadline is unlikely to be met. The sheer difficulty of coordinating so many separate, massive components, all of which must function perfectly, is immense. Critical components remain incomplete or untested, including the required functional spacesuits and the specialized heat shield for Starship's reentry.
So a lot of hurdles still to clear.
The ambition is high, but the technical challenges are currently outpacing the schedule.
Let's circle back one last time to the biggest theoretical challenge: bridging general relativity and quantum mechanics. The sources mention issues with quantum interpretation and public perception.
Quantum mechanics is perhaps the most widely misunderstood branch of physics in popular culture. Concepts like the observer effect are frequently pulled out of context and misapplied to everything from self-help psychology to telepathy. Scientifically, however, the math works perfectly.
We use it every day.
We use QM to design everything from lasers to MRI machines. Its predictive power is phenomenal and verifiable.
So if the math is sound, where do the scientific difficulties actually lie in linking it with GR?
The scientific difficulties lie in the non-intuitive nature of the concepts and the limitations of our experimental domain. For instance, concepts like wave function collapse. The moment a particle stops being a fuzzy cloud of possibility and chooses one definite state upon measurement defies our everyday experience. Or consider Bell's theorem, which confirmed non-local correlation.
Can you explain non-locality simply?
Non-locality means that when you measure a property of one entangled particle here on Earth, its twin, even if it's across the galaxy, instantly assumes a corresponding property. This simultaneous action fundamentally breaks our macro-scale idea that information transfer is limited by the speed of light.
So GR and QM are in direct conflict there.
GR says nothing can travel faster than C, but QM implies certain correlations happen instantly across vast distances. This foundational tension is exactly why unifying the theories is so hard. And the ultimate theoretical goal remains the theory of everything, but the lack of data limits progress.
We can't build the experiments we need.
Exactly. The conditions required to observe the effects of quantum gravity, either extreme energy levels far beyond what current particle colliders can generate, or extreme gravitational fields deep inside a black hole's singularity, are inaccessible to us. This means theoreticians are forced to rely heavily on mathematical consistency rather than physical verification.
To wrap up this extensive deep dive, we've clearly seen that the black hole is truly the central driver for the next era of physics.
We started with simple Newtonian concepts, watched the idea be dismissed 3 separate times, and now we are grappling with fundamental, unavoidable conflicts between gravity and the quantum world at the event horizon.
And the power of modern detection techniques, from adaptive optics to the Event Horizon Telescope and LIGO, is revealing a universe that is far messier and more complex than those pristine Schwarzschild and Kerr solutions predicted.
Especially with the existence and complicated migration patterns of those intermediate mass black holes.
Right. Stellar physics keeps throwing curveballs.
General relativity has passed every major observational test, from the subtle frame-dragging effects around Earth to the massive scale dynamics around SGRA. Yet the quantum questions persist. The black hole remains both the ultimate laboratory for GR and the ultimate roadblock for the completion of physics.
So what does this all mean for you, the listener? We've traveled from a 1700s math problem to the very real plans for settling in lunar caves. We've confirmed the sheer power of gravity through gravitational waves and learned that the quiet center of our own galaxy is, in fact, a gravitational battleground.
Indeed. We've seen strong evidence that our galactic center is far more dynamic and complex than we thought, potentially hosting a secondary massive black hole spiraling inward due to dynamical friction. If our own central environment is this volatile and complex, hosting multiple dark gravitational beasts of various masses, how many other nearby galaxies are hiding similar hierarchies of black holes? And what does that mean for the long-term gravitational stability of the local group of galaxies over cosmic time, where these behemoths constantly interact, potentially stripping stars and triggering violent events in the galactic suburbs? That's definitely something for you to mull or explore on your own.